Introduction for control of planetary rover vehicle. It is one of the requirements on the communication link between a planetary rover vehicle and its control center are mission dependent and will differ among, for example, exploration mission to Mars, the rear side of the moon, or on the equatorial region of on the front of the moon. The operation of a rover vehicle will also depend on the characteristic of the data link, ranging from direct remote control to full autonomy.
So, for our mini project problems, we have to determine the stability of the rover vehicle design, and we have to use the board plot to determine the gain and phase margin of the system. So we need to use the GS and K value, which is 500, and use the MATLAB to get our board diagram plot. So before we key in or insert the GS and K value, we need to multiply the K value with GS and expand the equation purple. Solution for our board diagram. So we have the magnitude and phase diagram for the board plot. So to determine the phase margin, first we have to see the magnitude graph and observe the graph that cross the 0 dB and make a straight line to the phase diagram and see the line of the phase diagram that approach to the negative 180. So that's it, the phase margin as given in the diagram. And to determine the gain margin, we need to see the phase crossover from the phase diagram and make a straight line to the magnitude diagram and see the gain margin that approach to the 0 dB line. So we get the result. The gain margin value is 4.97 dB at 7.8 radian per second, and the phase margin is 18.1 degree at 5.86 radian per second.
Okay, for the next question for 7B, the question asks, you are required to design a compensator lead or lag so that the phase margin will be at least 35 degree. For this your design, you are allowed to use Skylab or MATLAB for your work. Okay, for this, sorry, for my group, we use the MATLAB. Okay, so you can see this is for gain crossover frequency, straight line for the phase margin, and also the center, the point of the 180 degree for phase for straight line up to the positive, we call the gain margin. So this one for the calculation for the 7B, you can see this is for the general equation for the lead cascade compensative network. We call the GCS equal to S plus Z over S plus P. Z is about 0 and P is pole. So this is my equation. For this equation for the I expand and we solve 500S plus 750 over S plus 4 until 80. So the equation asks assume the K equal to 500. Then the very important is pool must be higher than 0. So if this question for this one is the system, right? The system. So this is a closed loop from GCS and GS until the output, and then we solve this is a for phase margin. The formula is phase maximum equal to sine -1 alpha minus 1 over alpha plus 1. How to get 32 means that how we get 32 means 18 plus 50. 50 is the safety margin from this part. Okay, safety margin must be an compulsory to plus 15 degree for the phase margin to get alpha, and then you calculate and answer for alpha is 3.5316. Okay, continue. For the gain margin, we can get the tau. The formula tau means omega m equal to 1 over tau times square root of alpha. How to get omega m? Omega m from gain margin. Gain margin from the frequency 7.8 radian per second must be change the radian per second, not to hertz for frequency, because this is that's why we use the MATLAB, easy to calculate. So how to get and then you calculate, and then until you get 0.06x82, and then you want to get a new dot plot, so you must do it. You must input substitute the value of alpha and tau from this part, GCS formula, 1 plus alpha tau s over 1 plus tau s. So s is the s domain. So you can get, you solve time only, just calculation multiply only, and then you get a new transfer function, 620.55s plus 930.575 over s plus 4 until x equal to 0, and then you can get the new transfer function. The k value is the 500, and then you substitute and then so on. You can get a new transfer function is 500s plus 750 over s power of 4 until 80, and then you can get a new dot plot.
Conclusion. From our observation, the system is stable. In order to determine the system stable or not, we use dot plot and LeapLab. So for our project, we use MATLAB to draw dot plot. It's easier to use MATLAB compared to Scilab. We said so because the coding used in MATLAB are much simpler and the value of frequency already converted to rad per second.